Welcome back to another permutations and combinations lesson. Today we're going to be looking at part 2 of combinations, and in this lesson we're going to be focusing on two terms, at least and at most, and we're going to be doing some examples that include those two terms. So before we get into the examples, it's really important that you understand what those two terms mean. So we're going to talk about some examples in context. So let's think that this quarantine is over, the restrictions have been lifted, and it's just time to get out and celebrate. And so you've decided you're going to get together for a big supper with some of your friends, and your parents have offered to give you some money, and they say, "How much money do you need?" And your response is, "I need at least $100." And if your parents hand you a $50 bill, you're probably not going to be too happy because you've asked for at least $100, which means you want $100 or more. Now you got your money in hand, and it's time to head out, and your parents say, "Well, wait, how long are you going to be gone?" And you say, "At most 3 hours." Well, if you show up at home 4 hours later, your parents aren't going to be too happy because you said you'd be out for at most 3 hours, which means 3 hours or less. So at least means it's that amount or more. At most means that amount or less. All right, let's take a look at some examples. So in the first example here, it says the student council decides to form a subcommittee of 5 council members to look at how funds raised should be spent on the students of the school. There are a total of 11 student council members, 5 males and 5 females. Exact same scenarios we would have seen in part 1. So let's just do some practice or review of those. So the first question says, how many different ways can the 5-member subcommittee be chosen if there are no restrictions on the number of males and the number of females? So if we look here, first example, no restrictions, there were 11 council members, and we're going to choose 5 of them. That gives us 462 council members. Well, what if we want exactly 3 females? So this is a question we would have had yesterday. If we want exactly 3 females, then that means we want 3 females and 2 males. And if we have 3 females and 2 males, that means we're going to have 6 choose 3 because there were 6 females. And there are 5 males, and we want to choose 2 of them. Again, notice that we've got the 6 plus 5 being 11, and the 3 plus 2 being 5. And so if we actually calculated that out, that would give us 20. 6 choose 3 is 20. And 5 choose 2 is 10. There would be 200 ways. Now, what if the question said at least 3 females? Well, if we think back to at least $100, that means you want $100 or more. So at least 3 females means we want 3 females or more. So on a 5-person subcommittee, that means we want 3 females, or we want 4 females, or we want 5 females. And then we think about what that means in terms of the males. That would be 3 females, meaning there's 2 males, 3 females, meaning there's 1 male, and then 5 females, meaning there's no males. And these are or scenarios, so we're going to be adding. So let's write all that out. So 3 females, 6 choose 3, 2 males, 5 choose 2, plus 4 females, so 6 choose 4, 5 choose 1, and 5 females, 6 choose 5, and 5 choose 0. Now, often if you're doing these questions, you are not going to see the 5 choose 0 because 5 choose 0 is just 1. So often if you're looking at this as, say, a multiple choice question, you won't see the 5 choose 0 there. But when we're looking at writing this out to check our addition, it's probably helpful to put that 5 choose 0. So whether you put that there or not doesn't matter. But especially if you're trying to count to make sure you've got your 6 and your 5 adding to 11, your 5 and your 0 adding to 5, sometimes it's helpful to write that down. All right, so if we go through and do the math, I'm going to let you trust me today that my calculator was working fine. The user knew what they were doing, but I'll write out those numbers for you. So 20 times 10, 15 times 5, and then 6 choose 5 times 5 choose 0 gives us 6. So 6 choose 5 is 6, and then 5 choose 0 was 1, so that doesn't change anything. If I add that all up, that gives me 200 plus 75, plus 75 plus 6. So that would be 281 ways. Now, again, you could certainly go back and check this with your calculator, but doing these questions, you're already going to be plugging this in quite a bit. So you can absolutely enter this in your calculator in one step, and I often do that. However, sometimes it's easier to break it down, because if you type 6 choose 3 in your calculator, the next time you go to type it out, especially if you have a newer calculator, you don't have to go back and retype 6 choose 4. You could just arrow up in your calculator, hit enter, pull that 6 choose 3 down, and just change your 3 to a 4. And the same thing with the 5 choose 2. Once it's typed in there once, just arrow up, choose it, and then enter down. Now, if you have an older calculator, you can also recall those just by typing second function enter. So second function entry, and it brings that information down for you. All right, so let's look at another example here. We're going to look at some cards. Again, remember in the last lesson we went through all the parts of cards and the suits and the different combinations of cards that are included in a deck of cards. So if you need a refresher on cards, first of all, I encourage you to play some card games. But second of all, just get out a deck of cards and kind of look through what's there. But the main part is that we have the 4 suits, and half of our card is black, and half of our deck is black, and half of our deck is red. All right, so consider a standard deck of 52 cards. How many different 5-card hands can be formed with no conditions? Well, we've got 52 cards, and we want a 5-card hand. Okay, so 5-card hands means we've got 52 cards, and we're choosing 5 of them. So that's a question that we did in the last lesson as well. So 598,960. Well, what if we want at least 4 cards? Well, in a 5-card hand, that means we want at least 4 red cards. So in a 5-card hand, that means we want 4 reds, meaning 1 black, or we want 5 reds, meaning 0 black. So if we write out that scenario, that gives us 26 choose 4, because there's 26 red cards in a deck, and 26 choose 1, or means add 26 choose 5, and often that's where we would stop. But again, you can also write out the 26 choose 0. 26 choose 0 is just 1, so it doesn't really change anything. All right, so 26 choose 4 is 14,950. 26 choose 1 is 26. And 26 choose 5 is 65,780. And if we add all of that up together, that gives us 454,480 different ways. Okay, so at least again is having that amount or more. We're going to look at most 2 kings. So at most two kings means we want 2 kings or less. So that means we want 0 kings, meaning 5 non-kings. So I'm going to put a little dash over top here. That means not king. So this is just like the complementary notation. Or we want 1 king, meaning 4 non-kings. Or we want 2 kings, meaning 3 non-kings. All right, so we're going to write out the scenario. Obviously, the more situations we have, the longer this is going to get to write out. Again, you don't have to write out that first part, the 4 choose 0, but I'm going to do that just so we can constantly see how they add up. So 4 choose 0, because there's 4 kings in a deck, and that leaves us with 48 other cards, and of those 48, we want to choose 5, or we have 4 kings, we want to choose 1 of them. meaning we have 48 remaining cards and we want to choose 4 of them, or we have 4 kings, we want to choose 2 of them, and 48 choose 3. Now if we write all of this out and add it all up, this 4 choose 1 is, or 4 choose 0 is just 1. 48 choose 5 is 1,712,300. I'll write out the numbers here. I won't read them all out. Again, as you're doing this, you don't have to be writing out every single step. I'm doing it just for the purposes of the notes. Often I would just put 4 choose 0 times 48 choose 5 in my calculator and write just that number down. So here we would have 1,712,300, and then we're going to add it to the rest of the numbers. And so if we add all of those numbers together, we're going to have 2,594,400. So obviously these questions involve quite a bit of mathematical work in terms of your calculator. So there's a lot of calculator use here, lots of opportunities to make silly mistakes. So always go back and double check your calculations. All right, we're going to look at one more example here, and that's asking you to find how many combinations there would be if there was at least one diamond. And so we're going to use what we already know and figure that out. So I'm just going to erase example number 3 here quickly, just so we have a little bit of space because this question is going to involve some work. All right, so let's take a look here. If we want at least one diamond, well, that means that we want one diamond, meaning 4 non-diamonds, or we want 2 diamonds, meaning 3 non-diamonds, or we want 3 diamonds, meaning 2 non-diamonds, or we want 4 diamonds and 1 non-diamond, or we want 5 diamonds and 0 non-diamonds. And you're probably already thinking that is a lot of calculator work, and it absolutely is. So if we write this out here, this is going to be 13 choose 1 and 39 choose 4, plus, again, because or means plus, 13 choose 2 and 39 choose 3, 13 choose 3 and 39 choose 2, or 13 choose 4 and 39 choose 1, or 13 choose 5 and 39 choose 0. So again, lots of combinations there. Now, if we calculate this all out, I'll save you some writing here, but if I put all of this in my calculator and I add it all up, I'm going to get 2,023,203. Now you're probably looking at that and going, oh my gosh, what if this had been a 10-card hand? Do I really want to add all of that up? And the good news is there's an easier way. So if we have at least questions and we're only being asked for one case, so at least one or at most one, these are scenarios where we can use something called the complement. So we're going to work through some examples here, looking at the 2 different ways we can do a question, and ultimately I'll show you the shorter way. So sometimes when we're using complementary outcomes, we can break down that workload or reduce the amount of calculations we're going to have to do using another method. And so that's using the complement. So if we go back to our first example where there was 462 ways that a 5-member subcommittee could be chosen from 5 males and 6 females, the students were asked to determine how many of the 462 possible subcommittees contained at least one female. So if we go back to our last set of examples here. We had, if there was no restrictions, there was 462 ways to choose males and females. We had looked at exactly 3 females. Well, what if we want to figure out all the ways there can be exactly 1 female? Well, that means 1 female and 5 males, 2 females and 3 males, and so on. And so all of the work is written out here. And we can do all of the calculations. So 6 times 5 is 30. 115 times 10, we got 150, and 275, and 6. Well, if we add all of that up, there's 461 ways that we can have at least 1 female. But again, just like that last question, that's a lot of calculator work. So there's got to be an easier way. So another student, Jasmine, looked at this and said that I can't do this. There's got to be an easier way. And I think I'm picturing a few people in my class thinking the same thing. So what she looked at is she said, okay, well, all of the ways that we can select these subcommittees, that would be 0 females and 5 females, 1 female and 4 females, and so on. And so really, all of these are the ones that we care about. The ones in brackets are the ones we care about. 1 female, 2 females, 3 females, 4, and 5. Well, that only leaves one scenario that we haven't considered. And so the total number of ways to select all the subcommittees is equal to the ways we have no females plus the way we have at least 1 female. So mathematically, if we think about that, that gives us the total equal to 0 females plus at least 1 female. And so if we take the total number of females and we subtract the ways that there's no females, that's going to give us what we want right there. Now, this only works when we're dealing with 1 missing element. So at most, and at least questions, we're looking for only 1 missing element. So if we think about this, we've got 462 minus the number of ways to select 0 females and 5 males. Well, what would that look like? 0 females and 5 males would be 6 choose 0 times 5 choose 5. Well, if we think about our math there, 6 choose 0 is just 1. Only 1 way to choose 0 females, and 5 choose 5 is also 1. So we end up with 462 minus 1, which is 461 ways. So significantly less work than having to write everything out. So in Jasmine's work, the outcome of 0 females and 5 males is the complement of the required outcome, at least 1 female. So in general, the number of ways for a required outcome, if we have only the 1 missing element, we can take the total ways, so no restrictions, and subtract the ways that we can have nothing. And so when we're writing the solution, if we were doing this question in any other way, we wouldn't have to write these first 3 steps. We would go straight to this part here, total number of ways to select the subcommittee minus the 0. So you don't need to write all of that other work out. All right, so let's take a look at an example then that uses the complement. In that earlier example, we were looking at least 1 diamond. Well, in this case, we're asking for at least 1 club. So consider a standard deck of 52 cards. How many different 5-card hands can be formed with at least 1 club? Well, the work would all be the same, whether we're using a club or a diamond, because there's still the same number of cards in the suits. But if we want at least 1 club, well, we think about how many ways we can have that. And so at least 1 club would be the way that we can have no restrictions minus no clubs. So again, if you think about that, if we want at least 1 club, that means we want 1 club, 2 clubs, 3 clubs, 4 clubs, or 5 clubs. And the only one that we're not considering is 0 clubs. So we're going to actually figure out 0 clubs and subtract it from the total. So at least 1 club is going to be no restrictions. Well, no restrictions is 52 choose 5 minus no clubs, which is 13 clubs choose 0 times 39 clubs choose 5. Well, we know from before that 52 choose 5 was 2,598,960. And if we subtract 13 choose 0 is just 1, and 39 choose 5 is 575,157. And so we're going to get that same total, 2,023,203. Now, this is, again, significantly less work than if we had to write everything out. So while you can do it the other way, and some people still choose to, knowing how to use the complement to save yourself some time is really helpful. All right, so yesterday I had asked you to think about why, I can't remember the exact example, but like 8 choose 3 was the same as 8 choose 5, or 7 choose 2 was the same as 7 choose 5. And today we're actually going to talk about why that is. So Bennett and Ryler have identical collections of vintage toy cars, and Bennett decides to select 2 toys from the 10 shown for the display. And so he goes onto the shelf and he wants to just pick any 2. So maybe these are the 2 that he's decided to pick. And so 10 choose 2 would tell him that there are 45 ways to pick those 2 trucks. Now Ryler decides he wants 8 toys. So he's going to select these 8 toys right here. And he knows the way that he can select 8 toys from a group of 10 is 10 choose 8. That's also 45. So interesting, 10 choose 2 and 10 choose 8 give us the same answer. So then the question is, why does 10 choose 2 equal 10 choose 8? And so I won't write out the answer here. I will just go through and explain it. So if you think about it, Bennett was choosing 2 toys out of 10, meaning while he's choosing to take 2 toys, he's also choosing to leave 8 toys. And Ryler is choosing 8 toys, meaning he's choosing to leave 2 toys. So I can choose to leave 8 in the same amount of ways I can choose to take 2. I can choose to leave 2 in the same way I can choose to take 8. Now we can show this mathematically as well. So if we use factorial notation, remembering that our formula for NCR is n factorial over n minus r factorial times r factorial. So if I want to write this out in factorial notation, 10 choose 2 would be 10 factorial all over 10 minus 2 factorial times 2 factorial, which reduces to 10 factorial times 8 factorial 2 factorial. If I want to write this out as 10 choose 8, that would give me 10 factorial over 10 minus 8 factorial times 8 factorial. So 10 factorial over 2 factorial, 8 factorial, which is really just the same as 10 factorial over 8 factorial, 2 factorial. So we can show this algebraically. And this is a question you could often be asked, is to algebraically show that 2 things are the same. Now this is using a specific example. We can also show it algebraically just using the formula. So if we wanted to come up with some other examples of equivalent combinations, we might think 12 choose 2 is equal to 12 choose 10. 4 choose 3 is equal to 4 choose 1. Or 18 choose 2 is equal to 18 choose 16. So if you notice the 2 and the 10 add up to 12. Now this does not work with permutations. Permutations is different because of the arranging, but with combinations this will work. So in the above example, we've got n choose r is equal to n choose n minus r. This is not given to you on a formula sheet, so this is just a property that you would need to remember. Again, if we use that other formation or other notation, n choose r, just written in a different way, is the same as n choose n minus r. So like I said, we can show these algebraically. Now this part D here is just sort of an extension. You're not going to be asked to show this one specifically, but it's important that you understand how this all works together. So n choose r, if I want to show algebraically that n choose r equals n minus r, well again, n factorial is n, or n choose r is n factorial over n minus r factorial times r factorial. So we want to show that n choose n minus r gives us the same thing. So if we start off with n choose n minus r, that's going to give us n factorial over n minus r factorial times n minus r factorial. Now if we simplify that down, that gives us n factorial over n minus n is just 0, and a negative r is a positive r, so r factorial, and n minus r factorial. And again, knowing that multiplication order doesn't matter, we can rewrite that as n minus r factorial times r factorial. Okay, let's take a look at one more example, and this is where you could be asked to solve for n. Now, when we're asked to solve for n, whether it's a combinations problem or a permutations problem, guess and check is always a method that we can use. But when we get into a lot of tests, especially if it's a multiple choice question, there's often going to be times where you're not asked for the answer. You're actually asked for a step or a part of the procedure. So it's important that you know how to do these both algebraically and then use your guess and check to check your answers. So the example we're given here, it says, during Pee Wee hockey tryout, all the players met on the ice after the last practice and shook hands with each other. There were a total of 300 handshakes. This is a very classic problem when it comes to combinations and looking at solving for unknowns. So we have a hockey practice ending. We got some handshakes happening, and there were a total of 300 handshakes. The question is, how many players were on the ice? So we want to figure out an equation for how to do that. Well, first of all, we have to ask ourselves, does order matter or not? I know that the whole topic's on combinations, so we already know it's combinations. But if this was just a random word problem, you have to ask that question. And so if I'm shaking somebody's hand, it doesn't matter whether I shake their hand or they shake my hand. We're still both shaking hands. So order does not matter in this situation. So order doesn't matter. And if order doesn't matter, then that means we're doing combinations. And so we don't know how many people are on the ice, so that's our unknown. Choose. Well, how many people are shaking hands at one time? It's 2. So we have n people on the ice, and we're choosing 2 people at a time to shake hands, and that totals 300 handshakes. All right. So there's often a mistake that's made where people will be so used to always just using the numbers that are given, and they'd write 300 choose 2 equals X. But that's not what the question's asking. We don't know how many people are on the ice, so we don't know how many people we're choosing from. We just know that we have 2 people and we're ending up with 300 handshakes. So the first way to try solving this is through guess and check. So you might say, well, I don't know, let's start with 30. So 30 choose 2, that gives me 435. That's too high. All right, let's jump then back to 20. 20 choose 2, that's 190. Okay, well, let's just split the difference. So 25 choose 2, there's my answer, exactly 300. So guess and check just means a lot of calculator work. But we can also solve for this using factorials. And this is the method that you need to be familiar with because, again, if this were a multiple choice question, you wouldn't be asked for the answer. That's too easy just being able to plug it into your calculator. They're going to ask you for a step in the process. And so we'll go through and look at that. So n choose 2 is n factorial over n minus 2 factorial times 2 factorial. And we know that that all equals 300. So we've got n factorial over n minus 2 factorial times 2 factorial equals 300. So the first thing we're going to do to solve is we're going to multiply both sides by 2 factorial. And so that then gives us n factorial over n minus 2 factorial equals 300 times 2 factorial is 600. So some of you might be thinking, okay, this looks familiar. I've seen this before. And yes, this is where we're going to break things down using factorial notation. And so if we break this down, remember we have to look at which one is bigger. Well, n factorial is bigger than n minus 2 factorial. So we're going to start by breaking that down. We're going to have n times n minus 1 times n minus 2 factorial all over n minus 2 factorial equals 600. And these will cancel. That gives me n times n minus 1 equals 600. If we multiply that out, that gives us n squared minus n minus 600 equals 0. And we need to factor, so there's maybe a little bit of guess and check here again, but our factors are going to be n minus 25 and n plus 26 equals 0. Now maybe not so much guess and check because we already did the question. We know what we're heading towards. If our middle term is only a difference of 1, that means our factors are only a difference of 1 as well. And so n minus 25 and n plus 26, that means that n equals 25 and n equals negative 26. Well, in the context of this question, negative 26 players on the ice doesn't make sense. So we have 25 players on the ice. So n equals 25, meaning 25 players. So like I said before, if you're given a multiple choice question, often you're not going to be asked for a number, you're going to be asked for the process. So you might be asked for this right here. This is quite common where you're asked for a step, and this is the one I often see is the question might say, while solving this question, the student gets to a certain step, and what does that step look like? And it might look like something like this, and their choices might be n squared plus n minus 600 or n squared minus n plus 600 and so on. But ultimately, they're looking to see, can you do all of this math and get to that step? And so in those types of questions, it's very important that you're able to do all of the math. So guess and check is great to get your answer, but we have to know how to do the algebra as well. All right, so those are all the questions for today. Take a look at some practice questions, and tomorrow we're going to be getting into some word problems and using both permutations and combinations. So thanks a lot, guys. Have a great day, and we'll see you soon.